Thanks very much, Ian, for that very nice introduction. I'm not sure I've ever had one quite as nicely put about being an interplanetary scientist. But it's a great pleasure to be in Liverpool today. I've never been to Liverpool before. I've been to the UK a few times. And I've had a very nice walk around town and enjoyed it very much, including the nice weather. When Samar, make sure we're in the right one, yes. When Samar invited me to give this talk, it's a little bit of a different title for me, because normally you can imagine when a scientist goes to give a presentation, it's of a scientific nature. So normally I focus entirely or almost entirely on the new results that we've gotten and how we got the results, and a lot of crystallographic information that sometimes is maybe not so interesting to most people. So it was a little bit of a challenge, and so I thought that I would approach it in a couple of different ways. But before I start that, probably a lot of you are thinking, you know all about Mars Science Laboratory and its recent successes on Mars. And probably most people don't realize that people on Earth have been studying Mars for well over 100 years. And it's intriguing to think about what it was like in the late 1800s when astronomers were beginning to examine Mars telescopically. And the Italian astronomers first observed canals in 1876, and Italian by the name of Schiaparelli published a map in '77 showing what he called canali. The remarkable thing, think about this over 100 years ago, he was quoted as saying, "The planet is not a desert of arid rocks, it lives." So you can imagine in the popular press of the day, people being so excited. And so the level of excitement probably exceeded today's excitement about Mars when people start to think about people on Mars. And indeed, the American astronomer Percival Lowell suggested that these canals, he was really getting interested in this theory of canals. He said that the canals were constructed by an intelligent race to trap melting ice from the poles to irrigate equatorial crops. So just imagine pulling out the London Times one day and said, Mars, intelligent life on Mars, watering their crops with snow meltwater. So interest in Mars has gone on for a long time. And as a result, we know a tremendous amount about Mars. And since then, since the late 1800s, we've continued telescopic observations. We have a wealth of information. Most of those are of spectral or spectroscopic and photographic nature. Later on, we sent orbiters to Mars, and we sent a number of landers to Mars. And so it's actually one of the better studied planetary bodies in our solar system. And some people say that we actually know more photographically about the surface of Mars than we do about parts of the Earth. Indeed, it's probably true. The reason all of these are important is they tell us about the history of Mars, the geological history that goes back about as long as Earth's, about 4.5 billion years. And I'll try to show you a little bit today about how they show us how Mars is different and how Mars is similar. It's really fascinating. And for me, and I think for many other scientists, these studies have not only informed us about processes on Mars, but by comparison, they've told us a lot about processes on the Earth. So what I thought I would do after receiving Samar's instructions is to give you a tour of the Mars Science Lab mission and give you a taste of some of the early observations from the Curiosity rover. I'll tell you what we've learned about Mars, not just from the Mars Science Lab mission, but just in general. And as of yesterday, I just checked, or this morning rather, we've gone 9.4 kilometers, and we've been almost 800 sols. And a sol is a Mars day. So it's essentially, if you're on Mars, you'll talk about, believe it or not, people say solaro instead of tomorrow. So we've been there almost 800 days. And in the end, just in the vein of showing you a little bit more detailed examples of the value of these kind of explorations to society, I'll give you some examples of some technological spin-offs from the instrument that we developed over the last 25 years that's now inside the Curiosity rover. So it's interesting, Mars is really unique. It's the only so-called terrestrial planet, Venus and Earth being the other, that has an atmosphere that preserves a really almost complete record of all of the geologic history. And there's some really interesting things to be learned about that. And I'll give you some little insights into why that might be. Why do we know so much about the early history of Mars? And it's relating to how different our planets are. Most of this relates to plate tectonics. And probably by now most people are familiar with the concept of plate tectonics. When I first took geology as an undergraduate, it was a fresh theory. And so it's remarkable, we live in remarkable times, because if I had gone to school 15 or 20 years earlier, the theory of plate tectonics was not accepted. And so we think of it as an accepted theory, and we have abundant data to prove that, but it's pretty new. It's still quite new. What happens on Earth is our continents drift slowly, really very slowly on the scale, to move very far on the scale of millions of years. The reason this happens is that we've got a thin crust. If I held an apple up in front of you, the crust would be analogous to the skin of the apple. It's very thin. And underlying that is a somewhat viscous portion of the Earth, due to the fact that the interior of the Earth is very hot. Indeed, the outer core is molten today. We have very good evidence from that fairly old Newton-style physics. And so the crust floats on this part that is convecting, much like water does in your teapot as you heat it up. You can see the little currents going. And the crust slowly moves along, and it's what we call subducted. As a result, what you see on Earth today is fairly fresh. We're constantly recycling most of the surface of the Earth. Mars is quite different. Mars was smaller, not nearly as hot, and so Mars' interior is solid, and so it doesn't convect. And so what we see on the surface of Mars today, in many cases, is the way it was close to the beginning of the formation of the planet, 4.5 billion years ago, which is really remarkable. It's a remarkable opportunity to be able to look down at a surface that has experienced all of that history. If you wanted to find a place on Earth that old, you would fail. You can find pretty old places, but most of the places on Earth, you won't even come close to the age of the surface of Mars. What does that allow us to do? We can see a variety of things that occurred very early in Mars history. And one of the things that fairly ancient astronomers knew about was this long canyon known as Valles Marineris. Here I have it superimposed on a map of the United States. It's huge. It's over 5,000 kilometers long, as much as 6 kilometers deep. On Earth, we would immediately assume that this was created by erosional forces, by water. But on Mars, it was created very early when the crust of Mars was just cooling, and it was cracking. And so this reflects very, very early processes. So it's what we call tectonic activity rather than erosional. So that's one of the beautiful examples. Another example of the differences that we're learning about Mars is the existence of very large volcanoes. And they're called shield volcanoes by virtue of the fact that they look like the kind of shields that a Roman soldier might carry. You can see that image here and here and here. These are long ago extinct, but they tell us that in the past Mars had localized volcanism, meaning localized volcanoes, like we have today. You probably read or you may have read in the newspaper lately that some people in Hawaii are having to leave their homes because of eruption of basalt, molten basalt that's going to go right through their houses. This ended long ago on Mars. Our largest volcanoes on Earth, for example in Hawaii, are about 200 kilometers across. In contrast, this volcano, this shield volcano on Mars, which is known as Olympus Mons, is on the order of 2.5 times the height of Mount Everest and about 600 kilometers across. It's massive. It's huge. How can they get so large on the planet Mars and so small on Earth? Is it due to erosion on Earth? Turns out it's not. The answer, once again, between Olympus Mons on Mars and Mauna Kea and the other shield volcanoes in the Hawaiian Islands, for example, lies again in plate tectonics. It's pretty interesting. I have a little example here. This is going to start moving for you. But you can imagine if you have a source of basaltic magma, liquid basalt, on Mars, there's no plate tectonics, the plates aren't moving, and it continues to erupt and erupt and erupt. On Earth, it erupts, the plates move, it erupts again. And so this accounts, actually in Hawaii, for the string of the Hawaiian Islands. And the largest volcanoes in the Hawaiian Islands are the most recent ones. And so that's why we get these very large shield volcanoes on Mars and these much smaller shield volcanoes that occur in strings on Earth. So plate tectonics, again, has proven to be a very important thing showing us the differences between Earth and Mars. Just to orient you in the geologic timescale, both Earth and Mars are approximately the same age as far as we know. And we actually have been able to construct a geologic timescale for the planet Mars. And you might wonder, how in the world can we possibly do that when we don't have any rocks to speak of? We have a few meteorites from Mars, but we don't have any rocks to date the planet Mars. And it turns out that it's possible to date the planet based on the size and the density of craters. Very early in the solar system's history, there was a very high density of bombardment of large bolides. And so if you see a region on Mars that has a lot of large craters and there's a very high density of craters, it's an older terrain. The younger terrains have smaller and fewer craters. You might wonder, fine, how do we calibrate that? And we're fortunate because we were able to travel to the moon. And so the moon suffered the same kind of bombardment, and we were able to essentially date the surfaces on the moon using modern isotopic methods and calibrate the density, the size and density of craters. So that allows us to construct this geological timescale. And you can see we start at 4.5 billion years. For about the first 8 to 10 million years, 800 million years. Not good at math in front of you, I guess. For about the first 0.8 billion years, let's do it that way, we have pretty good evidence that the surface of Mars was wet. And I'll show you some pictures in a minute about that. But actually there's evidence for liquid water having existed on the planet Mars. And evidence suggests that the water was probably near neutral, the kind of water that if you were really hungry on a camping trip, you could drink. Near neutral, probably not high dissolved solids. So a lot of people who are interested in this kind of thing think that this water may have been habitable. If you try to find life, evidence for life on Earth prior to 3.7 billion years, you're going to be very hard pressed. It's at most single cell. And so to find that kind of life, evidence for that kind of life on Mars is virtually impossible for us now. There was a fairly rapid transition that we see in the rocks to much more acidic conditions, much less habitable. And there was deposition of a lot of sulfate minerals. One of the primary minerals that was deposited during this time was magnesium sulfate, or Epsom salts, something my grandmother used to soak her feet in. There's a lot of Epsom salts on the surface of Mars, deposited during this more acidic, less hospitable time. But you can see about 3.1 billion years ago, all of the fun ended on Mars. And it turned into what is still a fairly dry, but not completely dry, as you'll see in a minute, and quite cold environment. So very inhospitable. Not necessarily uninhabitable, but very inhospitable. For the last 3 billion years. We really don't have a very good geologic record on Earth over this time scale. So it's remarkable this is what we have to deal with on Mars, and we have a pretty good record of it. So we proceeded to study Mars using a variety of rovers, and probably most of you know all about the Curiosity rover, which landed here in Gale Crater, but there were a number of different rovers that landed earlier, and I would imagine most of you would be surprised to know that the first two landers on Mars were the Viking landers in 1976, and it's incredible that we were able to put together the technology to send something to Mars, land on Mars, and actually do a lot of very valuable experiments. We learned a tremendous amount. These were the first experiments that initially suggested that there was life on Mars, and they've been later reinterpreted, and the conclusion is that they don't suggest life on Mars. But there was one sent near the poles, and the two so-called MER rovers, Spirit and Opportunity, were landed in 2004. Remarkably, I believe their planned lifetime was 3 months. And you can see that Opportunity is still going after 10 years. Many people on the project call it the Energizer Bunny, because it just keeps going and going. And it's likely that NASA will keep operating this until it stops, because we're just gaining a huge amount of information every week from all of these. So Curiosity launched here in 2012. I began working on this project in about 1989. And for those of you students in the room, if you want, when you think about something and you want it right away, just remember all good things to come to those who wait. And if you work on it and persevere, we finally were able to get our instrument on the Mars Science Lab after many years of working. And the opportunity exists for you today to do that. But after quite a while, in 2004, we were chosen to be one of the instruments on the Curiosity rover. And I'm one of the investigators on the X-ray diffraction instrument, and I'll tell you a little bit more about that. But the Curiosity mission launched the day after American Thanksgiving in 2011 on actually a fairly small rocket. It's an Atlas V rocket, and you'll see a picture of it in a minute. It took 8 months to get to Mars, had a very complicated landing. And some of you, I think, mentioned to me that you saw the 7 Minutes of Terror movie, which really was not an advertisement. It was designed to convince you that this is probably not going to work. It's incredibly complicated, and I'll give you a little bit more information on that in a minute. The one interesting difference between this and everything that's gone before is it uses a nuclear power source, so we don't have to rely on solar power. So we can operate day or night, winter, summer, and indeed we've taken great advantage of that. We actually have, for the most part, too much power, or enough power, all the power we need. The main mission, remember the MER rovers, the main mission was 90 days. Our primary mission was 687 Earth days, which is 1 Mars year. And we've gone beyond that, and like the MERs, I assume that we'll continue operating this until things stop working. And right now, everything is working. So everything is still working after well beyond what we call the nominal mission. So the day after Thanksgiving,
T-minus 15 seconds.
all the families and all the scientists went to Cape Canaveral
T-minus 10,
to watch
9,
our instrument
8, 7,
at the top
6,
of that rocket.
5, 4, 3, 2, 1. Main engine start, 0. And liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
It still gives me goosebumps to watch that. It was an incredible experience. If you've worked on something for 10 or 15 years and you finally get it up into the top of that rocket, it was a great day. And it was really nice to be able to share it with our family. So we knew then began the long trip to Mars. And at the top of that rocket was the Mars Science Lab. And this is just a quick schematic picture for you, showing you a list of all the 10 instruments on the rover. There's a variety of cameras, there's a brush, there's a drill. The body of the rover is the CheMin instrument, which determines mineralogy, the SAM instrument, which is a very complex chemical and isotopic instrument. I'll tell you a little bit about that. And there's an instrument for measuring weather and one for measuring radiation, but it's a tremendous rover that we now have on Mars. And almost immediately, we began operating it. And the radiation detecting instrument started operating. And I know a topic of discussion is often lately sending a man or a woman to Mars. And I hear from so many people, yes, we're going to do that. And what do you think about that? And I think that I wouldn't want to be on that spacecraft. This is the output from the radiation detecting device as a function of time from shortly after launch until shortly before landing. And you can see these significant, note that this is on a log scale, so every unit is times 10. You can see these very large radiation events due primarily to solar flares. And you quite often, if you have a cell phone, you probably notice once in a while, the news will tell you your cell phone service will be disrupted because of a solar flare. Here, it's going to do a lot more than disrupt your cell phone. And there's really no good way to shield for these high energy events. And so this is one of the issues that astronauts traveling to Mars would have to deal with. And you'll see in a minute what it takes to shield this, and it's more than we can do with a spacecraft. So after the 8 months, beginning of August 2012, Curiosity entered the atmosphere, and I've got a little simulation of it. It was a very complicated landing, and I mentioned the 7 minutes of terror. It was all done, we say, autonomously. There was nobody on Earth with a little joystick driving that, telling it what to do. Because the delay at that time, I can't remember, it was 5 to 7 minute delay time. So by the time you turned the steering wheel, it would have crashed. It had to do all of the landing autonomously. So it was in charge, and it was programmed, but it also was monitoring the surface. So it came in, I'll show you a little video of it, but it came in, jettisoned heavy weights. It has a heat shield on it, and many people think Mars doesn't have an atmosphere, so there's no problem. You're not going to burn up. Well, there's enough atmosphere to cause tremendous heating, and there's also enough atmosphere to allow us to use a parachute to slow down. The parachute deployed at supersonic speeds, so it's the largest hypersonic parachute ever used, and it slowed the capsule down enough. It's communicating with the ground to see where the ground is, and it drops what's called this powered device, this so-called sky crane. And the sky crane is a rocket-powered device that lowers down to the surface of Mars, and as it gets close to the ground, unbelievably, it lowers Curiosity down on a set of cables. And so you can see why many people thought it was not going to succeed. It was an incredibly complicated, detailed and complicated thing, and it was done all remotely it did it. So this is what it looked like. This is a simulation. Pretty interesting. So it's heating, getting frictional heating from Mars' atmosphere. It's guiding itself. It's going to pump the hypersonic parachute. And it will drop the heat shield. That's important. There it goes. We began taking a movie at that moment, which I'll show you. There's the rover. And the sky crane will deploy, the rockets fire. Now it's under rocket power. Parachute goes away to crash land, hopefully far away. This is monitoring the surface. The rockets are actually guiding it. Again, as I said, we're actually taking a movie of this while it happens. We have a real high-definition video that we downloaded, and I'm going to play it for you in a minute. So it lowers it down on these cables. The sky crane, which is still half full of rocket fuel, releases, ideally to fly as far away as possible, because we don't want the rocket fuel to contaminate all the instruments. So now we're ready to start doing something. But here it is, this is what it really looked like after we dropped the heat shield, with superimposed on that the audio from mission control. And at the end, you'll hear a lot of cheering. And I was at Jet Propulsion Lab at the time, and we could have blown the roof off.
Thrusters have been re-enabled. We will control our attitude on shoot.
So
we
watch.
are decelerating.
There goes the heat shield.
Risk mode under
About 10 kilometers
parachute.
accelerated.
This is real video.
We're at 150 meters
Not
per
a
second.
simulation.
Dynamics phase. Come back again with wrist mode dynamics.
We actually drove through
Risk
this
mode is
dune
nominal.
field later, a couple
We're
of months or so later.
Leads active.
Valid range.
Net filter converged with a velocity correction of 0.7 meters a second. We've acquired the ground with the radar. An altitude of 8 kilometers. Heat shield has separated where we found the ground.
Expand tones due to earth occultation as expected.
We're standing by to prime the Emily engines in preparation for powered flight.
So it's still under parachute.
We're down to
now.
90 meters per second at an altitude of 6.5 kilometers and descending.
Flight EDL, we got some Tweedo warnings. It is in battle forward mode, so I should power through.
Director of Communications at this time. We may have lost it already. We're down to 86 meters per second at an altitude of 4 kilometers and descending. We've lost tones from Earth at this time. This is expected. We're continuing on Odyssey telemetry.
There's 3 different signals we're looking for confirmation.
Ground solution equals minus 10.8 meters. Vertical velocity of minus
We are priming
82.8
power
meters per
semi
second.
start enabled, standing by for back shell separation.
So back shell separation is when the parachute goes away
Signaled Odyssey is still strong.
and the rockets fire.
We are in powered flight.
That was pretty exciting when we heard that they were in powered flight.
We're at
because
altitude
we know
of
it.
1 kilometer and descending.
We're making progress.
70 meters
You'll
per
see
second.
one of the rocket engines coming from the
Signaled
side.
Odyssey
Air.
Down to 50
Remember,
meters
it's
per second.
guiding itself to the ground.
500 meters in altitude.
And in the end, you'll see the rockets
Standing
actually
by for
shooting
second.
up a lot of dust. We really didn't plan this.
Constant velocity accordion nominal. Altitude
we
error
didn't
of
expect that.
5.9 meters.
We found a nice
There,
flat
see
place.
the dust?
We're coming in ready for sky crane.
So the rocket blast
Down to
is
10 meters per
actually
second.
disturbing
40 meters
all the
altitude.
dust on the surface of the planet. There comes one of the rocket engines on the side.
Sky crane has started.
So now it's lowering down on the cables.
Descending at about 0.75 meters per second as expected. Expecting bridle cut shortly.
Signaled Odyssey remains strong.
So we're communicating with it
Tango
via
Delta nominal.
one of the orbiters going around the planet. They don't know it yet, but it's on the ground.
UDLCOM configured.
Review stable.
That's the ground.
Review stable.
They'll figure it out.
UHF is good. Touchdown confirmed. We're safe on Mars.
Yeah. So there were 400 of the science team in a large room at the Jet Propulsion Lab listening to this, and oh, what a night. It was incredible. Just about blew off the roof from our cheering. And we knew then that we had, hopefully, a couple of years of really exciting times ahead of us, so we could finally start to use our instruments. So this is where we landed, and this is where the Curiosity rover landed, and you can see this dark area, and that's actually a result of the rocket blast blowing away all the covering on the surface of Mars. When you look at Mars, the red planet, it's red because it's covered with red dust, which actually is a real problem if you want to study it from afar, because most of what you see is red dust. If you're using spectroscopic methods, a lot of your signal comes from the upper a few hundred micrometers. And that's the red dust. So we've blown it away here. This is where the parachute and the little thing holding underneath it, the back shell went. This is where the sky crane flew away as far as we could get it and exploded. It was still probably half full of rocket fuel. And then there's that heat shield that you saw drop away. So we landed here, and we spent some time looking around, taking advantage of the fact that we'd essentially used a fire hose to blow all the dust off the surface. And even for those of you who aren't trained in geology, you're probably pretty good geologists, because you can tell from where you're sitting that we're looking at 3 different types of rocks. We've got this light area here that's heavily cratered. We've got this little bit darker toned area here that's cratered differently, and then this very smooth terrain here. And so we initially drove to this point to take advantage of the fact that in one point we could really check out the geology of all three of these areas. To give you an example of what we just landed on Mars, it's generally assumed to be about the size of a Mini Cooper, a new Mini Cooper, much bigger than the old Mini Cooper. And this is a picture of it at Cape Canaveral before it was put on the Atlas V with a couple people for scale. So it's quite large. It's by far the largest rover ever put on another planet. Almost immediately we started getting pictures like this, which were spectacular. My instrument room was right next to mission control. So any time of the day or night when we started getting data, we could go into mission control and be the first people on Earth to see these pictures. Here you can see in the back Mount Sharp, which is the mountain at the center of Gale Crater. You can see these rocket blast areas that cleaned away all the dust to allow us to get a good picture. There's a little shadow of the rover. And I always love showing this because it's very pertinent to today's society. It's as if we held out our cell phone camera and took a selfie, and then we photoshopped out the arm. But it's beautiful. Look at the peaks in the background of Mount Sharp. And so it's just so remarkable. And you can see here, I mentioned that the rocket blast threw up a lot of dust and material, and you can actually see it. You can see all these little pieces of stuff, all these rocks and debris lying on the top. It was not expected that we would have this problem, and it actually damaged some of the instruments, but they were weather instruments, and they're instruments of the sort that we had duplicates of, fortunately. So nothing else was damaged. This is one of the pictures that got a lot of press, and it's a remarkable panorama of Mount Sharp, showing these layers and these buttes and canyons, very reminiscent of the southwestern United States, near where we were. And one of the problems with all the pictures you see on Mars is they never have a scale. There's not some guy standing out there for scale. But we were able to do a little bit of figuring out, and we figured out that that little dot right there is the size of a Mini Cooper. So it's a massive panorama, just a beautiful area. And so we were going to spend the next few years driving along these, trying to get up to these layers that essentially record the past history of what happened in Gale Crater and on Mars in that area. I mentioned earlier that Mars has an atmosphere. It most definitely has an atmosphere. It's very thin. Surprisingly, it also has weather. This is a plot of the data from the temperature measuring device, so-called REMS, Environmental Monitoring System. It's measuring the temperature of the ground underneath the rover and of the air 24 hours a day, constantly. It's also measuring the humidity. And you can see what a horrendous place it is. We go from, at this time of year, a low of about minus 70 C, it's frigid, up to close to 0 C during the day. You can imagine what kind of stresses this places on all of the rover components. And so there's this huge change. And there's always a little bit of a lag in the ground temperature, but it's really fascinating to see how this changes from day to day and from season to season. Another example of how there's weather is, there's a picture of clouds over Meridiani taken by one of the MER rovers. And these clouds, we know from spectral data, are composed of water ice and CO2 ice, dry ice. So you actually have weather in clouds. Remarkably, you have, as you know, and we've known for a long time, polar caps. And this is a picture of the North Polar Cap in October, and you can see it's getting smaller and smaller as we go from October to January to March. So that would mean this is the North Summer. And what's happening is the CO2 ice at the pole is sublimating. And sublimating is, maybe you don't have as often frost-free refrigerators or freezers in the UK. If, everybody has a frost-free freezer in the US, and you can have an ice tray, and if you leave your ice tray in there for months and months, the ice cubes gradually just disappear. And so sublimation is what happens when you go from solid to vapor, passing melting. So that's what's happened here. The CO2 has sublimated away. here's some interesting data pertaining to wind. And this is air pressure. And the air pressure is phenomenal on Mars, the variations. This is on the 31st Martian day. We can see that we had we have a nice peak during the day. Seem to be about to lose my battery. I've got a spare. I have a nice peak during the day and then at night. And so we have this large variation from day to night everywhere on the surface of Mars. And it's similar to what happens on the Earth. This pressure change from day to night drives essentially a tidal wave of wind across the planet. So you can imagine if you're on a part of the planet that is here and another part is here, the pressure is going to blow from this part of the planet to this part. So you can actually get quite strong winds on the surface of Mars. Now the atmosphere is thin. It's about 140th that of Earth's, but these pressure variations drive pretty strong winds. The difference here is kind of interesting between Sol 31 and Sol 93, and this is a reflection of the sublimation of CO2 raising the overall Martian atmospheric pressure. So Mars definitely has wind. If you don't believe me yet, check out these pictures of dust devils. These are the kinds of things we see in the summertime on farms in the central United States. And these were movies taken by the Spirit rover. And you can see they just fly across the surface, and sometimes more than one at a time. And you can, if you look at the surface, you see all of these disturbed areas here that reflect the multitude of events that have occurred over recent time on Mars. So this is very important observation, because when we think about the processes that shape the surface of Mars, it's completely different than Earth, and it's something that we're not very good in geology at thinking about, at considering. On Earth, we're used to fairly short-term processes like floods and rivers and the oceans. And on Mars, we have a situation now, remember, that we've had pretty much the same climate for the last 3.1 billion years. So when people on Earth say, oh, wind could never do that, they're thinking in Earth terms. Because when wind does that for 3 billion years, you can do a lot. So it really takes a lot of imagination. It's an interesting exercise, and it's very difficult. We often say you have to think outside the box. You can't use Earth systems always as your analogy. So we were really excited. Finally, in October, we were going to get a sample into our instrument. And you can imagine, with all of the moving parts on the rover, the people in charge of operating, and it wasn't the scientists, they won't let us drive. The engineers they want to make sure that everything's working smoothly. So it was quite a while before we were able to put a sample inside the rover. And the first sample we chose was this sand dune here, a place called Rocknest. And the nice thing about that, one of the reasons we were excited about it is finally we're going to get a sample of this global dust that's covering the whole planet. Because we really don't know what that was, or we didn't know what it was. And we've also got more local material just blown in, so it's a fine sand and dust. And we got that into our instrument, and I'll never forget the day that we dug it, sieved it, and put it into our instrument and got diffraction data. You might wonder, why do we need this kind of information? I talk about X-ray diffraction in mineralogy, and I've got just a fairly simple example to emphasize to you why it's important to know mineralogy. If you simply know chemistry, that tells us what elements are present in a material. So we might have a chemical map of the entire planet, and it really wouldn't tell us what minerals were present. What we need to know is what structures they're in. So to give you an example, diamond and graphite, the black material inside a pencil, are both carbon. And if you ignored how the atoms are arranged in a periodic way, they're the same. Chemically, they're the same. But as you can imagine, the reception you're going to get when you give your fiance a nice chunk of graphite. Here, dear, I gave you some carbon. I think I'll get a new husband. The thing that sets them apart is how they're arranged. The carbon atoms are arranged completely differently. And it's the structure of the material that determines properties. And it's that tells geologists all about what's happened in the past. And so the structural arrangement, the crystal structure of diamond and graphite is completely different. Probably every one of you would agree, yes, it must be completely different, because here we have the hardest material known. There is no harder material. And one of the softer materials, one of the softer natural materials known. And the difference between them lies in how their atoms are arranged. So we use mineralogy. The reason we want so desperately to know mineralogy is because we, geologists, read the history of a planet by looking at the rocks and what minerals are in those rocks. And so if there's diamond in a rock, it tells us something very different than if there's graphite in a rock. So it's a very important piece of information, completely beyond knowing that it's carbon. Minerals also can tell us whether water was once present, because some minerals require water to be formed. Very important piece of information. They tell us about the chemistry of the waters. Was it potentially habitable or not? And they give lots of information about temperature and pressure. So we got the sample into our instrument. You might be saying at this point, if it's so important to know mineralogy, why did it take so long to put X-ray diffraction on Mars? The reason is that it was a technological nightmare. If you come to my laboratory, you will see this instrument here. It's about the size of a double-wide American refrigerator. It's about the size of 6 UK refrigerators. 550 kilograms. Has very large power requirements. So you can imagine, for the longest time, nobody even thought about sending something like this to another planet or even to the moon. So we had to deal with the large mass, the power requirements. In addition to that, when you do these kinds of experiments in the laboratory, you have to do fairly elaborate preparation of the sample. So we had a lot of problems to overcome in what ended up being about 20 years between the time we thought about this and the time we started doing it. Really the key to overcoming this, and if you're interested in the science behind it, you can delve into this. But essentially, the key is using what's called a CCD detector. And if you have a cell phone and you have a camera in it, its detector is a CCD, a charge-coupled device. And this is just a real fancy, expensive version of one of those. And it allows us to get information both on chemistry and allows us to get information on how the X-rays are scattered and diffracted by our sample that tells us about what minerals are present. And so the sample prep problem we overcame by using a little sonic vibration device. And this is essentially, we just have a sample in between a thin film of 2 polymers, and we pulse it with a little vibrator. It just makes a little beep noise. And as it does that, the sample powder flows. And so we've done very easily here what is very difficult to do in the laboratory. So we overcame most of the sample problems with this device, and we overcame the other problems by making the instrument very small. I didn't tell you how close that was, that the distance between the X-ray tube and the detector is 18 millimeters. So it's tiny. So in the end, we went from a double-wide refrigerator to a large shoebox size instrument. And it's on the Curiosity rover. This was one of the best days in my scientific career. The day that we got the first X-ray diffraction pattern from Mars. I'll never forget it. We worked over 24 hours waiting for the data to come down. The data came up on our screen. It worked. After all this time, it worked. And through a happy happenstance, these data came down on the 100th year anniversary of the discovery of X-ray diffraction by Max von Laue. Now, I've told you about the power of X-ray diffraction and what it can do for you. And if you don't think this was a pretty big deal 100 years ago, or 100 years before 1912, 2 years later, von Laue got the Nobel Prize in Physics for the discovery of X-ray diffraction. And 2 years after that, one of Liverpool's own Barkla received a Nobel Prize in Physics for something similar. So it was a fantastic time in physics, but this was a huge discovery. Consider that what we know about the makeup of solid materials is primarily been determined by application of X-ray diffraction. And so it's been a tremendous boon to our society to have this technique that we can apply to any solid crystalline material. So we had these data now, and I had the pleasure of analyzing the data, and it was maybe anticlimactic, but not surprising. We discovered that the mineralogy of this dusty sample was very similar to the soils that we find on the flanks of one of these shield volcanoes in Hawaii, and indeed they're all similar. Very young soils, and they contain typical minerals that you find in basalts, plagioclase feldspar, some pyroxenes, olivine. The interesting thing was that this dusty, sandy material contained a large amount of glassy material. You might say, who cares about glassy material? The reason glassy material is important is that in the presence of water, fine-grained glassy material would just go like that. It would disappear in months to years, and we've had billions of years. That tells us that that dusty material on the surface has not been in contact with water, basically ever, or it wouldn't be glassy material any longer. So it was a pretty exciting thing, and now we know what's in the dust. I mentioned I'd show you some other evidence for the presence of water in the past, and this is one of many beautiful images that we've gotten from orbit. This is 300 meters, and these are layered rocks that look for all the world like the kinds of things you see in Utah in the United States. And most people assume that these were deposited by water. They certainly look like sedimentary rocks. Keep in mind, they could have been deposited by wind over eons, over billions of years. But we do have another piece of information. This scour, where the rockets blew away all the dust, was really fascinating. We didn't go too close because it was contaminated by the rocket blast, but we went close enough to get pictures, and you can see here that it looks a lot like the kinds of things we see on Earth, where you've had streams weathering rocks into pebbles, or eroding rocks into pebbles. And indeed, here's a comparison. On the left, the Mars rocks, it's a 1 centimeter scale bar, and a similar thing on Earth. We call these conglomerates. They're normally used to infer the action of flowing water over a long time, long enough to round all the cobbles into nice little round cobbles. And so this was a pretty exciting thing. I have shown this to several audiences around the world, including to some people who are expert in wind-related processes, and they say, you can do that with wind. And if they think you can do it with wind based on their Earth experience, probably you can when you've got a few billion years. So I'd say the verdict's not out yet. Now, so we have evidence that Mars, it sure seems like Mars once had water. And we have pretty good evidence. I'll show you some more. What happened to it? This is, I think, one of the more fascinating things that's come out of our studies of Mars, and it tells us a lot about Earth. Because I often hear people say, isn't Mars kind of an end state of what's going to happen to Earth after global warming? And I'll let you be the judge of that after this. But what's interesting about the Martian atmosphere is that this is Earth, and we've got, as you know, we have a magnetic field, and that's generated by the fact that the center of the Earth is very hot. We have an inner solid core and an outer liquid core, and they counter-rotate and they generate a magnetic field. And the magnetic field lines, this is an artist's picture of it. And Mars, on the other hand, was never that hot. It didn't differentiate. It does not have a molten core. It may have once had briefly one. And so this is a picture of measurements of essentially north and south poles. You can see they're all local little tiny remnant magnetic fields. So you don't have anything like this on Mars. If it did have a dynamo, something to generate the magnetic field, it's gone. And indeed, it looks like it may have had one briefly. Why does this matter? Here's why it matters. This is fascinating. Credits of ESA. We've got the magnetic field around Earth, and our solar system is constantly being blasted by solar wind, day and night. And every once in a while you have even more, and you get these solar flares. And you can see when this solar wind comes to Earth, the magnetic field acts somewhat like a Star Wars deflector shield and deflects that solar wind around it. And we've had a magnetic field on Earth, as far as we know, since the beginning of the Earth. When it hits Mars, it essentially strips away the atmosphere. And so it's likely that Mars once had an early magnetic field that protected it for maybe the first upwards of 1 billion years, probably less. That magnetic field decayed, and gradually then Mars' atmosphere was stripped away. So when you hear about people talk about the Goldilocks zone, Earth is in just the right place. It's not too hot, it's not too cold, everything's just right. And you start to realize when you look at the contrast with Mars, there's a lot more to it. And so you might have somebody in the Goldilocks zone with no magnetic field, and its atmosphere would be long gone, stripped away. So it's really fascinating how you can put all of these pieces, contrast with Mars together to learn something about Earth. Another atmospheric difference that's been found recently, there's a tremendous amount of interest in this, is whether or not there's methane in the Martian atmosphere. And there were observations from Earth that suggested, yes, there was methane, small amounts. And so there is an instrument on the Curiosity rover specifically designed to look for methane at very, very low detection limits. And there were a couple of papers in Science and Nature talking about the fact that methane on Mars is very important. And the reason it's interesting and people get excited about it is that if there's methane on Mars today, that means it's being produced today, because it has a lifetime in the atmosphere of just a couple of years. So I say here, 0.6 to 4-year lifetime. So if you see it today, it was produced in the last 4 years, which is pretty momentous. One of the primary things that forms methane on Earth is microbial action. So now you see why it's so exciting for people to have thought they saw methane on Mars. Unfortunately, if you care, some people care, people ask me, what do you hope to find? I said, I hope to get the data and let the data tell me what's there. Unfortunately, the SAM instrument has found no evidence of methane on Mars at very, very low detection limits, on the order of 1 or 2 parts per billion. Doesn't necessarily rule out life on Mars, but it certainly doesn't support it. So we moved on after we analyzed, the rover analyzed these sand dunes, and we moved on to rocks. And here's these beautiful, what look like sedimentary rocks, and you can see these things we call crossbeds, and they indicate sediment transport by water or by wind. Actually, these look most like what we see with wind. And we prepared to drill here, and you can see it's a really fascinating surface. There's lots of cracks and little raised ridges where things have been deposited. And we drilled a couple of holes. The one on the left is a test hole. It was drilled with this 1.6 centimeter bit. It's just like the kind of thing that you would use if you were going to drill a hole in a concrete wall. It's a fancy carbide bit. The idea is it just produces a powder. This is the hole that we used, and this is the powder that we obtained from that hole. And that powder was then put into our X-ray diffraction instrument from this, what we found later was a mudstone. And this is the diffraction pattern we got from that. Of course, unless you're really into this, this won't mean anything. But the cool difference is, you can see down here at the low angles, there's just lots of brightness here that's not here. This is due to a clay mineral, to clays. The kinds of things that if you go outside in your backyard, in your garden, and you dig up the soil, you'll find a lot of clays. And the reason this is important is that clays will not form without liquid water. So this tells us that this material has had some interaction with liquid water. So there's perhaps some of the strongest evidence we have. This material simply cannot form without liquid water because there's hydrogens and H2O molecules in this material. So it's really strong evidence that whether you can do it with wind or water, we know that there was a period when we formed what we call hydrous or H2O containing minerals. So that was really an exciting thing. So kind of to wrap up the kinds of things that we've learned about Mars and the contrast with Earth, we know that we do know it had early volcanism, so it was active in the beginning, but it's always lacked plate tectonics, and it does today. We learned about the importance of a magnetic field to having an atmosphere. If you have a strong magnetic field like we do, it's our Star Wars force field protecting us from solar wind. And Mars hasn't had one probably for at least 3 billion years. We've learned a lot about the relative importance of weathering and erosion by wind, primarily on Mars, and water on Earth. And we found no evidence for either past life or existing life. So we both started out wet. That's pretty clear. But because we differentiated and our Earth was quite hot due to a variety of things, one of which is the presence of radioactive elements, we differentiated, Mars didn't. So Mars lost its magnetic field, it's lost its atmosphere, it had no movement of plates because the crust is solid. And so we get to look at the original surfaces, which really is a tremendous present that it's given us. But you've seen, obviously, Mars still has weather, and so most of the processes are wind-related. And so even with the few samples that we've gotten to date, we've done mostly driving, unfortunately, that we've already recorded this transition from a wet environment where we form clay minerals to a very dry environment where you can have fine-grained material on the surface of Mars that's probably been there for billions of years and hasn't reacted. So we've had a very dry environment. So now I want to just say a few words about spin-off. So we've got this incredible instrument that we shrank from this size to this size. And there are tremendous, you know that there are a lot of spin-offs from space science research, from ESA and from NASA. But I just want to focus on our CheMin instrument. And we started, as I mentioned, about 89. The first few years, we just had this instrument hanging off a lab instrument, which was very large, over 500 kilograms, the same as the one I have now. We then got it smaller, and in 2004, we had a small device that 2 people could carry out to the field. Here we're in Death Valley right here, testing it. We always need to take it to very interesting and exotic places to test, because it's much more fun. So we took it to Death Valley. We took it to the Arctic, to the Antarctic. It was quite enjoyable. It's a fantastic couple of years. We now have this instrument, and what's really nice is one of the men on our team, who was a postdoc with us, developed a suitcase-sized X-ray diffraction instrument. So we now, instead of this thing that's 550 kilograms, have a suitcase size, and I could stand here in front of you and hold it. This is a picture of it. Weighs about 15 kilograms, runs on batteries, will run 4 hours on a charge, and it communicates wirelessly with your laptop, so you can put it out in the field to make measurements, and you can go in your tent and protect yourself and communicate with it wirelessly. So this is tremendous advance. Here it is in the dry valleys of Antarctica, making measurements with its computer sitting next to it. There have been a number of these sold. As of 2010, about 100 instruments have been sold. It actually won the gold medal in 2009 as the best new instrument at the Pittsburgh Conference, which is the largest instrument conference in the United States. I don't know about the world. But it's used in a variety of different applications. And I won't go into all of them. You can imagine the advantage you might have of taking this suitcase device out into the field in Southeast Asia, for example, and analyze malaria drugs that are being given to people and discover that they're made of cornstarch and that they're not doing anything for the people. And there's a lot of effort in that, in the pharmaceutical and in the FDA. It's used in mining. Here it is 7 kilometers down in a potash mine. You can find out exactly what you have right now. There's a big advantage to being able to take the instrument to your samples instead of taking your samples home and analyzing them. And I'll just give you one example. We were in the Arctic sampling, looking for hydrated salt minerals, and we collected some hydrated salt minerals and analyzed them and found that they were they consisted of sodium chloride and magnesium sulfate minerals. That's nice. The epsomite was one of them. We put this material in a bottle and said, well, we really need to take it home and do it right on the lab instrument. 2 weeks later, we're back from the Arctic. We analyzed it in my lab. There was no sodium chloride and no magnesium sulfate. They had reacted together inside the dry bottle. It was dry. It reacted together to form a completely new material. It's a magnesium sodium sulfate chloride mineral, which we're familiar with. But you can imagine you'd taken it back and you'd write a big paper about all these new materials you found in the field, and they weren't there at all. So it's really a powerful ability to take this into the field. Finally, one last example, which is pretty interesting. In a historic country like yours, there would be a lot of examples. There is the development based on this similar technology of an instrument called Duetto. And it is a small, non-contact instrument. It's small enough to go, all the pieces, the tripod, et cetera, can go into 3 of those little suitcases. So you can easily ship them on an airplane. And they can be used to analyze all manner of artifacts and things. And the advantage is you can come right up to some priceless antiquity and not touch it and determine the mineralogy and the makeup of the material on the surface. So here's Giacomo Chiari from the Getty Institute putting this up close to the wall in King Tut's tomb, which obviously you can't bring back to your lab because it's on the wall in the tomb. He's analyzing the makeup of the pigments on this, something that's never been done before. And now they're starting to understand what pigments they used, what went down first, what's happened to cause them to degrade with time. This is all a direct spin-off from the Kemin instrument. And here he is back in his lab looking at the exterior of the Red Shroud mummy in the Getty Museum. He works for the Getty Museum. You can even use it to analyze paintings, and he's done this very many times. He's one of the leaders in this, and he's worked with us. We've worked with him. And you can actually go up and analyze a thin piece of a painting and look at the makeup of any little spot on the painting. You can detect forgeries. You can see modern pigments, for example. So he's done a tremendous amount of work with this Duetto instrument directly as a result of all of this work that we did over the years to make a compact instrument that you can put right up against it. So hopefully I've shown you a couple of ways where these planetary missions are benefiting society and really telling us a lot about Earth. The more I got into it, the more I was surprised how much Mars informed us about Earth, not just Earth informing us about Mars. And in fact, sometimes we get the wrong information. And that there have been a number of technological spin-offs. And just one final thing, for the young people in the audience, I always like to emphasize, if you're sitting in the audience saying, wow, I'd really love to do that someday, but I guess it's not possible. It really is possible. We had a number of people on our project at the Jet Propulsion Lab who were undergraduate students who worked day in and day out, night and day with us. And I asked many of them, how did you get involved with this? How did you get this such a great opportunity? And they said, oh, I just asked. So if you're interested in this, pursue it. It's one of the most exciting things you can ever do as a scientist. And thank you so much for having me here. It's a pleasure.